All right, so now we move into one of the more fun concepts in Algebra 2 is dealing with the imaginary numbers, the complex number system. So all real numbers that we've been dealing with, rational, irrational, integers, whole numbers, natural numbers, those are all part of the complex number system. The real numbers are a subset of the complex numbers. Then we have the non-reals. So the existence of the reals indicates we also have the existence of non-real numbers. And up until now, every time that we have had the square root of a negative number, so every time that we've had the square root of a negative number, we've just said not a real number. Okay, so now we're going to deal with that not a real number issue. And we can actually still do all of our arithmetic operations with non-real numbers. Okay, so we first have to define what is the imaginary unit. Well, it's a number that when I square it, it equals -1. Okay, within the real number system, there's no number that does that. Okay, there is no number in the real number system that when I square it equals -1, because every time I square +1 or -1, I still get +1. So we can define it. Instead, we can say that the imaginary unit is the square root of -1. That is our imaginary unit is. And if I square the square root of -1, if I take the square root of -1 and I square it, what happens when we square a square root? It cancels out the radical. So we are left with just -1. So the square root of -1 is a number whose square is -1. We define that as the imaginary unit I. Okay, so I is equivalent to the square root of -1. I squared is the same as having the square root of -1 squared. So I squared is equivalent to -1. So we use these two identities a lot with our imaginary numbers. Yes? Imaginary number shows up more in things like the next you would see it is with like calculus and vectors and that kind of stuff. There's a relationship with it between vectors and engineering. It's not exactly a one-to-one relationship, but it's similar in how it behaves. Okay, and then we'll have to be able to deal with the imaginary number when we are doing more complex calculations with quadratics, but also higher degree polynomials. And the existence of the imaginary numbers have a very real effect on the graphs of all the different polynomials when we have them. And so that'll be part of a quarter 4 unit that we look at. Okay. So whenever we're trying to simplify a radical that has a negative radicand, we use -1 as one of those factors when we break it apart. Okay, we use -1 as one of those factors, and then the identity that the square root of -1 equals I. So that allows us to then simplify all of our radicals, whether they're real or they're non-real. Okay, so using I notation to start, so I have the square root of -25. Okay, so we start by breaking it apart, and when we see a negative radicand, we immediately pull out that factor of -1. And so we can split this as the square root of -1 times 25. Okay, now, is 25 a perfect square? Yes. So we don't need to simplify it any further. We've got -1, which we can define as I, or the square root of -1 is I, and we've got the square root of 25. So we have, my pen would work. Of course, now my pen stopped. Yeah, 1 second. And there's a very specific way that we write it once I get the battery to work. No. So hold on. I want to be very clear in how this is working out. Okay, so we can split this here, right? So when we're splitting apart our radicals, when we take the root, we've performed the operation. The radical then goes away. So the square root of -1 equals I, okay, the imaginary unit. We don't leave it in the radical. It is its own thing. The square root of -1 equals I, okay? So we have I. And then the square root of 25 is 5. So I have I times 5. Now we have a very special way that we write numbers when we're dealing with the complex numbers, in that the imaginary unit always goes at the end, okay? So we would write this as 5I. So I like to draw it stylized so it doesn't look like a 1 or anything else. So I try to make it very clear that it's an I. So when you're writing it, especially on your assessments, make very clear that it's an I. Yeah. So -1 is always a factor. So if I had the square root of -2, I would pull out the -1, but I would still leave the 2 in the radical. And we'll see some of that very shortly. Okay. So with B, I can automatically pull out the -1, but is 32 a perfect square? No. We need to split it more. Largest perfect square factor of 32? 16. So we've got 16 and 2, okay? So again, when we're splitting these apart, I have the square root of -1 times the square root of 16 times the square root of 2. Okay, this is how we're simplifying our radicals. If I can take the root, I perform the operation, the radical goes away. On any parts that I can't take the root, then the radical stays where it is. So the square root of -1 is I. The square root of 16 is 4. Okay, and the square root of 2 is the square root of 2. Right? Okay, now we need to be very, very careful about how we write this. Yes, it is 4 the square root of 2I. But you need to be very clear that that I is no longer inside that radicand. Okay, it needs to be outside. So a lot of places, what you'll see instead is they'll write 4I root 2. Either one of those is fine. Either one of those is fine with me, okay? As long as if you do the first one, you're very, very clear that the I is not inside the radical. Typically, yes, but a lot of times you'll see this because sometimes it gets shoved inside that radical again, and it's not inside the radical anymore, okay? And there'll be some other ways in which, yes, it will go at the end even after a radical because of it's slightly more complex with the equation. But I'm okay with either one of these. If there's still a radical, if you want the radical at the end and the imaginary unit in the middle, that's fine with me. Okay? You could. Yeah, that would be fine. Okay? All right. Why don't you go ahead and give C a shot? So we've got a negative, and then inside our radical, we got -1 and 121. So we've got negative square root of 1, and the square root of 121. Is 121 a perfect square? Yeah, square root of that is 11. So I've got a negative, I've got an I, I've got an 11, so it's -11I. So it's negative, so the expression itself is negative, it's all multiplication. You can imagine that this is just a -1 being multiplied by my equation here. So I've got -1 times I times 11. Multiplication is commutative, so we just put it in the order that's consistent.
understand what the imaginary numbers like.
So there'll be operations in which we start with imaginary numbers and we end with very real numbers. And the imaginary numbers also show up when we do our graphs of polynomials.
What exactly is an imaginary?
It is the number, the square root of -1. So the real numbers are something that's very tangible and real, but that's not even a small portion of all of mathematics. It's not just the reals.
It's not a number that we don't know. It's just a number that doesn't exist.
It's a number that does not exist in the real plane.
So and then maybe you just like on the number line.
Right.
How come we couldn't just put I or what?
Well, because we didn't take the time to talk about I yet.
Yeah, but so like let's say we were to get something like this on the test and we just learned this. What stops us from not getting confused when using I? Do you know what I mean? The directions.
Yeah, the directions, and I mean, just now it's part of our repertoire, so that'll be moving forward. Yeah.
So now we have no more no solution problems.
Nope, no solution and non-real numbers, two different things. No solution means there is no answer. The non-real numbers is just a type of number.
Okay, so no more non-real numbers.
No more non-real. Well, no more putting down non-real number as a answer. Now we can actually specifically simplify the non-real number. Yes.
How much work would you want us to show for one of these equations? All of that, or?
So for simplifying a radical, something like this, that's sufficient, from here to there. Okay. If the number's already a perfect square, again, just there to there is fine. Does that make sense? Okay. So just breaking apart. If you need to include more of the steps to make sure you're clear, go for it. If you've got it from the first step to the last, then you're fine. Okay. Now, here's what often causes a problem with non-real numbers. Okay. So when we have the non-real numbers and we apply the product rule or the quotient rule, they don't behave exactly the same way. Okay. Whenever we have a non-real number, we have to put it in I notation first before we do any arithmetic. I can't add, I can't subtract, I can't multiply, I can't divide until it's in I notation, because it has this weird side effect of giving us the wrong answer if we don't do that. Because when I multiply two negatives or I multiply two positives, I get the same result. And there's no way for me to distinguish that ahead of time. Okay? So for example, if I had the square root of 4 times the of -4 times the square root of -9, I cannot apply the product rule and then multiply -4 and -9, because that gives me a positive 36. Okay? But when I multiply those two together, it's not actually a positive 6. So let's put both of these in I notation first. The square root of -4 in I notation would be what? So I have what is the square root of 4? 2i, right? So I have 2i. And then what is the square root of -9 in I notation? 3i. Okay? So I have 2 times I times 3 times I. Okay? 6i squared. And what does I squared equal? -1. No.
Where did you guys get that? So it's just 6?
So I is the square root of -1. If I have the square root of -1 times the square root of -1, that's the square root of -1 squared, right? This is all I squared. I squared, okay? The square root of -1 squared is just -1. So when we're doing our multiplication, when I end up with I squared, it equals -1. So I is the square root of -1. I squared is -1. So when we apply this product rule, 2 times 3 gives me 6. I times I gives me I squared. Since I squared equals -1, it equals -6, which is not 6. It's still a real number, but the sign's different. So when we are doing any of our operations on non-real numbers, we have to put it in I notation first. I notation first. Then we can add, then we can subtract, then we can multiply, then we can divide. We can do all of that stuff after we put it in I notation. Yes. All right. So this, I should probably go to A. All right. Yes.
So the final answer would be -6.
Mm-hmm. All right. What is the square root of -3 in I notation?
But that's not a.
Would it not just be
Radical 3i, radical
It should be -3i, and then negative.
Is 3 a perfect square? No.
-3 squared i.
So I have a -1 and I have a 3, right? So I have the square root of -1 times the square root of 3. What's the square root of -1 equal? I. So I have I times the square root of 3. We want to do the same thing with -5. -1 and 5. -1 and 5. Yep. Always -1 because it's the square root of -1 that equals I. The square root of 1 is just 1. So I need to deal with the negative. So we've defined the imaginary unit so that we can deal with the negative. This wasn't something that's like, well, what if we just made an imaginary number? No, they came up across these circumstances and they said, well, I need a way to deal with this. Okay? I need to be able to do something with this result that is showing up. Mathematics is always born out of necessity, not out of boredom. Despite how bored you may be sometimes, it is born out of necessity. And so they said, I have to deal with the square root of -1. Okay? So then they came up with the imaginary unit and then saw that this still flowed through a lot of the other algebraic processes and still held true to all the mathematical axioms, and then other features started to arise out of it. So now I have I times the square root of 3 times I times the square root of 5. Okay? So we can multiply the radicals together, the square root of 3 times the square root of 5. 15?
Oh, I 15i squared. Or
15, yeah, I did square root of 15.
The square root of 15 times I squared.
But that wouldn't turn into.
I squared equals -1. Again, so I is defined as the square root of -1, right? We use our power rule.
So it's just going to be negative. So it's going to be
Negative.
We square both sides.
Yeah, negative square root of 15.
So I squared equals -1.
So this is negative square root of 15.
Negative square root of 15.
I was writing, have been writing.
Mhm. Okay.
Can I go up and be the spokesperson?
Not today. I appreciate your enthusiasm.
Wait, so we were like,
Yeah.
Right? So what am I going to do with the square root of negative 36? Negative 1 and 36. It'll be what? 6i. So I've got the negative 1, I've got the 36, so that gives me I and a 6. And then what about the square root of negative 1? That's just I. 6i squared equals negative 6.
Does this get like a lot harder?
yes, of course.
No, it's more operations, but again, the math is all the same. So just like when we were solving our radical equations, okay, the first step was the only new thing. Everything else followed all the mathematical stuff that we've been doing all year. Here, the only new thing is the negative 1, right? Everything else is going to be consistent with all the other math that we've been doing. So the way that we combine like terms, the way we apply distributive property, how we can factor things, how we can simplify radicals, all of those steps are the same. The only thing that's novel here is this part. Everything else is consistently the same. Does that make sense? Okay, so we're just adding in one new detail to stuff we've been doing forever.
I don't know if somebody asked earlier, but why, when we put it together, it started off as a negative number, and when you put it in the radical with a negative 1, you change it. Why do you change it to a positive?
Why does negative 36 become a positive 36? Because I've factored out a negative 1. Negative 1 times 36 is negative 36.
On the test equation, you have to show the work from 6
So again, for something like this, that's you break it apart like you do your radicals, right? You show me breaking apart your radicals, you show me breaking apart your radicals, you include the negative 1. Okay? So that part's pretty consistent. Those intermediary steps just add more clarity as you're going through it. Now, the more steps you show, if you make a mistake, the easier it is for me to figure out exactly where that was. But if you go straight from here to just, the wrong answer, say you wrote positive 6, I don't know where you went wrong. Does that make sense? So again, the showing the work, that's not for me. Not really. It's for you. It's developing the skills and the processes and the reasoning ability to make it through each of those steps and to understand what you are doing. Okay? So when you're going through this, okay, even when you're just doing practice, and we start with this, okay? I'm gonna start from scratch, and I'm gonna have a little mental dialogue with myself while I do this, okay? So you kind of get an idea. All right, so I have the square root of negative 31, so I need to factor out a negative 1. So let me split these into negative 1 and 36. Well, I can now write those as separate radicals. I have the square root of negative 1 times the square root of 36. Well, the square root of negative 1 is defined as I. The square root of 36, that's a perfect square. So I'll go ahead and take that square root. Well, that equals 6. I'm also multiplying over here by another square root of negative 1. Well, that also equals I. So I have I times 6 times I. Multiplication's commutative. I can multiply in any order. So I can take 6 times I. Well, that's I squared. Well, I remember that I squared equals negative 1. So I have 6 times negative 1. Well, that just equals negative 6. So there's a lot of steps there. And if you're having that dialogue in your head, you don't necessarily need to write down all of those steps, but you should be having a dialogue in your head, or I guess technically a monologue, in your head of what you are doing. That's how you solidify your understanding of why things behave the way they do. And that's how you draw those connections between how you start, that process that follows, and the solution that you arrive at. Does that make sense? So if you're focusing on how much work do I have to show, you're missing the whole point, right? The whole point is to wrestle with the content and truly understand what the operations are and how these things flow logically. Okay, that's what the work is helping you demonstrate that logical flow and keep track of stuff so you don't have to juggle all those numbers in your head. Okay, I've been doing this a long time. I can look at that and I can get the answer off the top of my head in about 3 seconds. You guys have seen this for a total of 20 minutes now. I don't expect you to be there. So writing down the work is what shows you, what helps you keep track of all those calculations that you're making, keep track of all the parts of that internal dialogue until you get to your end result. Does that make sense? Okay.
How come you didn't pursue English?
How come I didn't pursue English? I was a journalism major for 2.5 years, so I almost did. My first year teaching, when I was getting my math certificate, I was subbing for a remedial English class, and the coach there tried to convince me to get my reading certificate instead of my math one. I was like, I don't want to read all these essays. I like the math much more. All right, so square root of 8.
You don't need a -1 for that. But
I don't, because it's negative.
split it into 4 and 4.
Yep, we'll split into 4 and 2.
Oh, 4 and 2. I'm slow.
Okay, what about square root of -2? -1 and 2. Okay, so again, just making that split, that's an important first step in just analyzing the structure and being able to see all the pieces. Okay, some of you don't need to do this next step, but many of you still do, just to understand where these things are breaking apart. Okay, so this is an important distinction that a lot of people are still missing in their math.
So when it's us positive, we don't need to use negative.
You don't need to use negative because it's not negative. Yep, only when it's negative. Okay, can we square root 4? What that gives us 2. So I have 2 times the square root of 2. Can I square root -1? I can now. What is it? It's I. The square root of -1 is I. Okay, I still have 2 radicals. Can I multiply those together? Yeah, what's the square root of 2 times the square root of 2? So I have 2 times I times the square root of 4. Can I take the square root of 4? Yeah, what do I get? 2 times I, it would be 4i. All right, quotient rule.
With this?
Mm-hmm. So before we apply the quotient rule, we want it in I notation.
Yeah. So you look for the top one, you go
5. No, not 5. Is it 15? What is it?
Let's just take out the I. Let's leave everything else for now.
okay, so -1.
I've got -1 and 125 over root 5. Okay, so if I pull out the -1 and I take the square root, I have I times the square root of 125 over root 5. What can I do with these radicals now? I can divide them. I can put them under the same radical. I have I times the square root of 125 over 5. Simplify the fraction. What do we get? 25.
I radical 25.
So we did radical 125.
Yep,
Wait,
Yep.
And we got
because that's our quotient rule. I've got a radical divided by a radical. The indexes are the same. So I can write them in one single radical with the numerator denominator, simplify that fraction, then simplify the radical.
I thought you had the square root of 125, not divided.
Well, it was the square root of 125 divided by 5, all in one radical. Yeah, yeah.
So it's 5.
So then we get 5i. Okay? All right, so those are all, for the most part, either purely imaginary or purely real numbers. So now we talk about the complex numbers. The complex numbers are numbers that consist of a real and an imaginary part. Okay? And we write our complex numbers in the form a plus bi, where a and b are real numbers, and then I is the imaginary unit. So again, real numbers are the subset of the complex number system. So all of our real numbers, you take 16, which is a real number, dealt with 16 so many times. I can represent it as 16 plus 0i. That is a complex number. We also had a lot of pure imaginary numbers. We can represent those as complex numbers where the real part is 0. 0 plus 3i.
So B is 0.
For the 16, b is 0.
But it's not always 0.
If it's a purely real number, b is 0 because you don't have the imaginary part. 0 times anything is 0. Okay? So what we're doing is we're taking the real number system and we're expanding it. And we're adding in more numbers. Okay? So within the complex number system, we write our numbers in the form a plus bi. Real numbers are complex numbers. Pure imaginary numbers are complex numbers. Okay? They are all part of the complex number system. When we perform our arithmetic, it's almost identical to the real numbers of addition and subtraction. It's almost identical to adding and subtracting radical equations, okay? Adding and subtracting polynomials. It's combining like terms. When we're in the complex system, our like terms start to also include, are they real or are they imaginary? So when we're adding complex numbers, we can add the real numbers together, and then we can add the imaginary numbers together. But I can't add a real number to an imaginary number. I can write the operation. I can say a plus bi, but I can't actually add together a and b because one of them is real, and then one of them is attached to the imaginary number. Yes?
Okay, I have a question.
I have an answer.
What is, like, you said, like, it's just not a number on a number line. So, like, what would that be?
It's actually a number on a different plane. So we have in one dimension, we have our number line, okay, where we've got 0, -1, and 1, okay? That's our one-dimensional number line. Then we move into two-dimensional, which is our coordinate plane, where we have x and y. And then we can identify ordered pairs such as 2, 1. Okay, this is our Cartesian grid. Okay, so that's our two-dimensional number system. There is another plane, it's called the complex plane, which is how we represent imaginary numbers or complex numbers. I can't represent complex numbers on this plane, okay, on my number line. Sorry, it's skipping around. Okay, I can't represent imaginary numbers on the number line because that's just real numbers. I can't represent it on the coordinate plane because that's two sets of real numbers. So we defined a new plane where the x-axis represents the real numbers. The x-axis represents the real numbers, and the y-axis represents the imaginary numbers. And so if I take a number like -6i, okay, I'm just going to grab that one. Okay, that's a complex number. The real part is -6. This a is -6.
So we'll eventually end up graphing this.
I used to have us do that. I took it out in favor of some other stuff because it wasn't as crucial. But you can. And then here we have our imaginary part. Since there's no number in front of I, what do we assume it to be? a 1, right? So b equals 1. So we would graph this just like we would on the coordinate grid. And I say, okay, I'll go left 6 units, 1, 2, 3, 4, 5, 6. That represents negative 6. And then the y-axis is the imaginary. So I go up 1. So this is the number, negative 6 plus I. And so we graph it just like we do on the Cartesian. Okay, but it's a completely different grid because we're dealing with a different set of numbers. So there you go. Got a little side lesson on that. All right. So we can add and subtract the complex numbers, and then we just want to make sure we write the sum or difference in the form a plus bi. So we add the real numbers together. What are the real numbers in my first sum here? Okay, so I'm going to add 2 and negative 3. And then what are the imaginary numbers? 3i and 2i. So if I take 2 and I add negative 3, what do I get? Okay, if I have 3 i's and then I add 2 more i's, how many i's do I have? 5i. Hey, if it works, it works, right? Okay, I behaves just like a variable does. That's it. We've got it in the form a plus bi. We'll see.
Oh my god, it's Friday!
I know. All right. All right.
So how do they both get I?
Because I'm just adding the parts together. Don't worry about it. It's distributive property is what it is.
Oh no. Wait, the test that we're taking next week is on 7.5.
We'll talk about that next week. Okay. Let's focus on our complex numbers today.
Oh, right.
It's like terms. Okay. So I'm subtracting. What do I need to remember to do?
Distributive property. 5i minus 1 plus I.
There we go.
Then it's negative 1i as 6i.
Negative 1 plus 6i. So this has a real part of 0. So 0 plus negative 1 is negative 1. Then 5i plus 1i is 6i. Okay. Same thing here. We want to distribute. So negative 3 minus 7i. Then what? Plus 6 minus I. What are my real numbers? Negative 3 and 6. What are my imaginary numbers? Negative 7i minus I. Negative 3 plus 6? 3. Negative 7i minus I? Minus 8i.
Wow. Wait, can that just be the test?
No.
Is it gonna become like?
We can multiply today.
What's the next piece?
Yeah, we're going to start. We can do the multiplying. We got time. Okay? Because we kind of already did it, right? So we're just multiplying. This is negative 7 times I times 3 times I. So I can multiply the negative 7 and the 3, and I get what? Negative 21. Man, why is this? And then what's I times I?
Wait, so then does that become?
So I've got I squared becomes negative 1, which means the product is a positive 21. If we have more than one term, we use our distributive property. So 3i times 2 and 3i times negative I. Minus 3i squared. And what's 3i squared equal? That's going to end up being a positive 1, right? Because we've got negative 3 times negative 1. So it becomes 6i plus 3. Now we need it in the form a plus bi. So let's rewrite it. 3 plus 6i.
Oh, so that.
I squared is negative 1. The square root of negative 1. Yeah. You could factor out a 3, but then you're just undoing your multiplication. That is its simplest form.
It can't be 6i plus 3i.
You have to write in the form a plus bi. 3 plus 6i. Okay? All right, real quick. Distributive property. 2 times 4.
Distributive property. No.
2 times I. Negative 5i times 4. Negative 5i times I. Yeah, I know. That's because I'm writing quick. Okay? Do I have any like terms I can combine? So that's negative 18i. Then we also have, hold on. Negative 5 times I squared becomes positive 5. Do I have any other like terms I can combine? 8 and 5 gives me 13 minus 18i. All right, we will finish up on Monday. You do not have any homework. Congratulations. Have fun. Enjoy your weekend.